Hello and welcome to another episode of Rust in Audio. Today I want to show you pointers and lifetimes in Rust. We will build kind of a slice object ourselves. And although usually you don't use raw pointers in Rust, I think it's very nice to understand how it works and to understand lifetimes. And you can benefit from raw pointers in very high performance loops. So let's have a look. I started with a test already. Here you see we just have a vector from with some elements, and we want to create a buffer class that can get a slice to our data. And then we want to have the possibility to index into the buffer. So if we get index 3, we expect it to be 3.0. So let's build the object. First we need a struct with the name buffer, and our buffer needs to contain the data. This could be the slice, but in our case we want to have the lowest type, so we use a pointer. You see this is pointer const, there's also pointer mute, both works, but for this example const is enough. And because our pointer is unsafe to use, we also need the length. Without our length, it will be hard to verify if we're still in the array. So now we implement the functions. The first function is from data. From data, and this here is a slice to F32. It looks like this. And the return type is self. You can also write buffer instead of self. Some people prefer that, but I like just to stick to self. So what do we need inside of here? It's the first thing is data. We can also say fill struct fields. Data is slice dot as pointer. Here you see as pointer returns a const pointer, as mute pointer returns a mute pointer, and there's also pointer range, which will give you the start and the end. That's also sometimes nice to use, but for our example we will just use the pointer, and the length is slice.length. So nice. As we learned last time, as is usually a keyword for something that is very cheap to do, and this is true here. As pointer can be used everywhere in your code. Basically, it's very, very cheap. All right. We see this is already working now. And the last function we need is index. So you also have the possibility to use this notation. But for simplicity, I just implement a function now. We need a reference to self. That just means by giving this reference here, we can access our members, our variables. And we need the index, that is the usize. The return type will be F32 then. You can also do a reference, doesn't matter for this copy type. And how do we index now into our data? We can, it's a pointer, so we can dereference the pointer. That's the first thing we can do. So the pointer points to this object or to this number. And by dereferencing it, we will get 0. Now this is red because it says dereference of raw pointer is unsafe and requires an unsafe function or block. That means when you dereference pointers, you usually don't know if you're still in the range, or maybe it's a null pointer. So let's add the unsafe block. And now we see, cool, This works already, so we should get 0. Let's run the test. And the test failed, that is expected. Yes, that should be the first element. But now we want to get to our index. So we need to add to the pointer. This is the add function. Adds an unsigned offset to a pointer. And then we go index steps in the array. So when we run the test, it works. That's great. The only problem here is we don't do any checks. So there are multiple problems with this buffer class now. The first one is we can access an address that is not in our array bounds anymore. So when we go to address 5 or 6, you will see, oh, it failed, and we received a value that is completely nonsense, right? We never specified this value anywhere. So now we are accessing a value that is not meant for us. And that's, in some occasions, this can be a security risk, or it can lead to undefined behavior. But for sure, we don't want to get a value that we never meant to access, right? So what we can do here is just have an assertion that says index has to be smaller than our length. And now this condition will always be safe, actually. So when we run this, it will crash and we get this panic. What you can do, what is usually a nice thing if you build something like this, to have a should panic test. And with this you can verify that no one deletes this assertion, basically. So you can verify that it's still safe to use. So we say test, I don't know how we call it now. And just do it like this. And now if we run this test, it should be okay. Yes. So it crashed, but this is expected, so the test passed. All right. Let's build this back to 3. But there is another issue. So this function is now safe to use because we do the bounds check. The other issue is here that we should check. No, that's all right. Sorry. The other issue is the lifetime. Okay, this slice here has a specific lifetime. So in our test case, the data object gets created here and has a lifetime until here or until here. Our buffer lives shorter than this, so this is all right now. But in case our data would be deleted earlier than our buffer access, we wouldn't get warned right now because we never specified that buffer has a specific lifetime. If you use a slice, that happens automatically because a slice has a lifetime. Here we have this problem. I will show you how that looks. So let's create a new scope, and create another data object. Then we can just override buffer here with the same. So now we override buffer to point to this data object. For this, buffer has to be mutable. And now we already have a problem, because here buffer will point to data, but data's lifetime ends here and it will be deleted. So what do we see here? Let's try it. Failed, and again we have a completely nonsense value. So this is now a situation that isn't so perfect. No one warns us that this data object is actually not alive anymore. And how can we improve this? This is where those lifetimes come in that are very difficult for beginners, but let's just add this lifetime A. And this is how it looks. You can also call it help or whatever, but usually the notation A, B, C, D is used in Rust. And now our pointer doesn't have a lifetime. Yeah, when you would have a slice in here, you could use it like this. Then we would use the lifetime actually, and it would be fine. But as we have no object that needs the lifetime, we somehow need to tell our struct, hey, please use this. So there's where phantom data comes in. It sounds a bit more complicated than it is, but phantom data is really just a zero size object. Yeah, it gets removed by the compiler, and it's really just to say, hey, this lifetime is used in here. Please keep it. And we also have to add the phantom data here. And this is just like this. And then you have to do this kind of double work that I never understood at the beginning. Yeah. So when we have the lifetime here, we also need to create it here and here. And this is a bit weird at the beginning, right? Like, why do I have to write it twice? But the thing is, here you kind of specify which lifetime this should be, and here you can give it a different name. So here we can also call it B, and that would work. Yeah. Or it becomes clearer why we do this if you have, for example, a generic value here, like a float, generic float. And then you do an implementation here that is just for F32, or an implementation block that is just for F64. We will look into this later. But then this notation makes more sense. Yeah, it's actually kind of useful. But at the beginning, just, you have to write it twice. So now we have our lifetime, all good, but it still works, our test. So we still need to point Rust to say which lifetime this actually should be. And this should be the lifetime of our slice. So let's add A here. And now we say we give it all the same name, so our compiler knows which lifetime it should use. Let's save this and check. And now it actually works. Great. You see it doesn't compile anymore. Yeah, when we hover over it, it shows data does not live long enough. And here, data dropped here while still borrowed. And here, borrow later used here. So that is great. Yeah, we get warned now that we do something that leads to undefined behavior. Okay, here you see the full error again. Data does not live long enough. So that's great. And this is exactly how slices work underneath, yeah. But if we remove this this scope now, so that data is still alive, you see it will work. And when we run our test, it succeeds. That's perfect. Let's delete this and just stick to our normal test. Yeah. We can remove the mute and the buffer. And that's already all for this day's episode. Yeah. Just to make clear, we used phantom data, raw pointers, and lifetimes. Yeah. Why can pointers be nice to use? It's just the best performance you can possibly achieve. Yeah. In a slice, you would index like this. Yeah. And this has additional bound checks again. Yeah. A slice also has a length. So this is if you use something like this, you can just get the maximum performance. But usually you don't need this. Yeah. So the general recommendation here is always go with a simpler solution until you need the performance. Yeah. And if you know, there I have a hot loop where I have a bottleneck, then you can go to something like this. Yeah. But I think it helps of understanding why lifetimes are such a bless in Rust actually, and why it's worth it to write it out sometimes. Yeah? All right. Thank you for listening. I hope you could follow somehow and you learned something. And see you again next week. Bye-bye.